Okay, good morning everybody. Great to see you all here. I think somebody was telling me it was the coldest day for a decade, and then I read in the news since 1908 or something like this. So there's probably some frozen people halfway here. Good to see you all this morning, and I hope you've enjoyed the school so far. Thanks again to our sponsors. I've got them on the screen there. And what I want to do is, yesterday I'm told that, for those of you in the room, you might feel like history is repeating here, but I didn't share the slides very successfully to those online. So I'm just going to quickly remind you of the how the school fits together. So forgive me for those who heard all this yesterday. But for those online, you can see this now. Hopefully it's working. No, it's frozen. Now it's working. It works after you click the button, not when you click the button. So just quickly, there's these 5 different aspects of the school that we include. So the insight talks are there to give you insight, surprisingly. The idea there is that you'll get an idea of somebody's career or their profession or their particular discipline of research or some industry aspect so to give you some context for everything that we're learning and using today. My volume on? Yeah, last time I didn't do the slides. This time I didn't do the volume. I'll go back one, because they really heard nothing. Good morning. See, it's cold. Even my brain's not working. And now the screen's not working. I'll do interpretive dance soon. Okay. All right, for those of you online, hopefully you can see my slides and you can hear my voice. Just a quick one about how does the winter school fit together. We've got these 5 different aspects. There's the insight talks, which are all about the perspective and giving you insight into people's careers or discipline areas or technologies or industry. They're experts from their field all over Australia and, in fact, overseas as well. And we've got lectures which are more about the technical information, making sure that we can equip you with the knowledge base that will instruct you as you want to develop your own innovations using microengineering and microfabrication. We've got practicals because we want you to get some hands-on experience and to be able to create things in the lab that you can touch and feel and take home, hopefully, and so you've got a bit of a context of what it's like working in the lab environments that we've got, including the clean room. The tours are for you to get your feet in the door of some industry and see how they're building their devices and what kind of industry is around the place, especially here at Mawson Lakes. We go for local tours. And for networking, and we've gone on about this the whole time, networking is by far the most valuable thing that you can achieve here. We've talked about multidisciplinary projects and collaboration, and so networking with others, getting collaborative teams around you so that you can deliver those more complex innovations is going to be interesting and important for your careers. So I've just said all that, but this is the general structure. This is yesterday's jigsaw puzzle, but you'll see we always start with some insight talks, and we're about to go to one now. We have lectures, then those practicals and tours, and there are chances for networking, and my encouragement to you is to make the most of them. Great to see many of you there at the dinner last night. This is today's session. We're going to kick off in just a moment with Heike from online. She's overseas at the moment, and I think it's very early in the morning. So Heike, hopefully you can hear me and you'll be wide awake. It always makes me nervous when it's that time of the morning for our speakers. And then we've got Scott here, who's from DSTG, and we'll have later the lectures from Mike Pye and Ben Johnston. Ben's all the way over from New South Wales. And so, and also the industry tour that will be on this morning is at Rapier. We've got about 2 spots left. I think 2 spots left. So in the break, race to Bell or wherever the sheet is and get your name in, and you can jump on that bus today. So, and tonight, of course, we've got the Optofab tour. That'll be fantastic. They've got some amazing facilities in glass, and I think you'll be inspired to go to the tour just from Heike's talk in just a moment. So and there's 2 spots left for that. So if you haven't, yes. Oh, there's 1, 2. Was that 3? There was.
Is that for Optofab or Rapier? Rapier. Oh, we've got the forms. Can you pass it?
Okay.
We could do a bidding war, yeah? We could do some fundraising. For
How much are you
ANFF.
prepared to pay? No. That was quick hands.
Sorry, it was Peter. It was Reiki, wasn't it? And I can't remember your name. Sorry? Nikos, thank you.
Okay, it's just something in the chat. Can you check the chat before I go?
I can see the slides, yeah. That's good.
Okay, excellent. So what I'm going to do now is introduce Heike. Now, I mentioned before that there are different ANFF nodes, and we're ANFF-SA here, but the Optofab node, we have two speakers actually from the Optofab node today, and later we'll hear from Ben Johnston from New South Wales, but right now we've got Heike Ebendorff-Heidepriem, who is a professor at the University of Adelaide, and she's waving, fantastic. And Heike and I have known each other for a very long time. We collaborate here in South Australia to do some amazing things in microengineering together. Heike has outstanding world-class expertise in glass materials and optical systems. And to avoid me, misquoting something here or just saying something like she's amazing, I'm going to read quickly her bio. So she received a PhD in chemistry from the University of Vienna in Germany and has held 2 prestigious fellowships. In 2001, she received the Weil International Glass Science Award and joined the Optoelectronics Research Centre at the University of Southampton in the UK before moving to Australia in 2005. Heike leads the Fibres and Photonics Materials Research Group at the University of Adelaide and is Deputy Director of the Institute for Photonics and Advanced Sensing. Some of you might know it as IPAS. Her research focuses on the development of novel optical glasses, fibres, surface functionalisation and sensing approaches, and recently, hopefully I'm not stealing thunder, she's made some fibres in space. So Heike, thank you so much for staying up late over there to speak to us. I'm going to stop sharing so you can share, and then the floor is yours. Let's welcome Heike.
Thanks, Craig. I can't share at the moment.
Can you allow sharing? Sorry, just a second, Heike. We'll get Belle to click the button.
Now I can share. Just a second. Just put this away. Can you see the screen?
That's great, Heike. Thank you.
Okay. Thanks, Craig, for the extremely kind introduction. So I try to stay awake and also stay on time. Let's see how this goes. So it's a really great pleasure to be virtually with you at this fantastic winter school, which Craig, Belinda's and many others have run for so many times. So I want to talk about my core expertise and research, the specialty optical glasses and fibers, fabrication and applications. See how I can move it forward? Yes, here. I'm sure Craig already told you about ANFF, that it has several nodes. Currently, you are situated at the ANFF-SA node, and there is also the Optofab node. It has several locations, and Optofab Adelaide Hub is located at the University of Adelaide, the North Terrace campus. And as Craig mentioned, there's an opportunity to see our facilities today at 6 p.m. So the outline of my talk is really 2 parts. First, the basics of glass and fiber fabrications, and then very few applications. So let me start with what is glass. Many people are familiar with crystals like table salt, quartz. A crystal has a periodic structure, and that means also long-range order. In comparison, glass like silica, which has the same chemical composition as quartz, has a random structure, let me get a laser pointer. So the crystal has a regular structure, glass has an irregular random structure, so no long-range order, and therefore the structure is really that of a frozen-in liquid. So what this means then, in contrast to crystals, where there is a sharp transition from the liquid to the solid stage, the glass changes gradually the viscosity from being solid to being in the molten, that means in the liquid stage. And this gradual change in viscosity is really the key for glass to be able to be shaped in an unlimited range of geometries. So if we now look from the point of the glass composition, then we can take the periodic table of elements and we can classify the elements in network former cations and network former anions. So like the silicon and the oxygen that form the backbone of silicate glasses, like for window panes. And then in between this network, there are the so-called network modifier cations. So if you look at this picture, then on the one side we have the silica, I already mentioned it a few times, is composed out of silicon dioxide. On the other side, we have the multi-component glasses, and they can be classified. So this are the elements for silica, multi-component glasses. They can be classified in a range of oxides, the borate, aluminate, gallate glasses, silica and germanate glasses, phosphate and telluride glasses, and a range of network modifier cations. Other glass type are the fluoride glasses made of zirconium fluoride and indium fluoride, and a third glass are the so-called chalcogenide glasses made of chalcogens, sulfur, selenium and tellurium as the anions, and arsenic and germanium as the cations. Then also for luminescent or coloration applications, the key elements there are the lanthanides and also the transition metal ions. Often a subset of the multi-component glasses are the soft glasses, heavy metal oxide glasses containing lead oxide, bismuth oxide and tellurium oxide, fluoride glasses and the chalcogenide glasses. So this is from looking at glasses from a composition point of view. We'll not go into details, just showing you that we make in-house a range of glasses, but we also use commercial glasses and even polymer materials at Optofab Adelaide Hub. So now let's look at from the point of view, what are now the properties of the different glass type I just mentioned. To understand this, I plotted here on the horizontal graph the so-called glass transition temperature. This is where we keep the glass to anneal out any stresses. This glass transition temperature scales roughly with thermal, mechanical and corrosion stability and with the melting temperature of a glass, and it scales inversely with the infrared transmission. On the vertical axis, I have the most important optical property, the refractive index, which scales with the optical nonlinearity. So if you now populate this with the different glass types, you see here there are these different glass types. I put here the legend, and the reason is that unfortunately in this corner we don't have a glass. Nature does not allow us. So if you now go through the glass types, there is silica, has a high TG, therefore high durability, and therefore it's of interest for high power fiber laser applications. On the other side, we have the chalcogenide and fluoride glasses. They have the mid-infrared transmission, However, that means they also have low glass transition points and therefore lower durability. However, so for the fluoride glass, nevertheless, the advantage is not only the mid-infra transmission, but the low index and therefore high-power laser applications in the mid-infrared. We'll give there examples. And for the chalcogenide glasses, they show the so-called high nonlinearity, which is of importance for the so-called supercontinuum generation. Now in the middle are the heavy metal oxide glasses. They have sort of an interesting balance of these various properties. So low temperature processing, high crystallization stability, high rare earth solubility, and the index is somewhere in the middle. This combination of properties make them really suitable for easy processing, and we use them a lot for testing new concepts, and I will show the one or the other example. Okay, now I talked about composition, I talked about properties, now a few slides on glass fabrication technique. The most widely technique is the so-called melting quenching technique. This technique is used to make window panes, household and labware glasses. And so it works as follows. First, a mixture of crystalline raw materials is made according to the required glass composition. This mixture is placed in a crucible. If we make glasses in smaller quantities, like at Optofab Adelaide hub. The crucible is placed in a furnace, heated up, and these raw materials, they first melt, the lower melting crystals they melt, and the higher melting crystals they dissolve in the glass melt. So that after a few hours a clear glass melt is obtained, the crucible is taken out of the furnace and the molten glass is cast into a preheated mold, preheated at the glass transition temperature. Then so the trick here is now that the glass cools down quickly, therefore quenching from the melting temperature to the glass transition temperature, where the glass is hot but solid. And because of this quick quenching, the atoms don't have enough time to move around that they can form crystals. Now then the hot but solid glass goes into a annealing furnace, cools down slowly to the room temperature to avoid the crystallization. And here you see a photograph of a gold crucible. You see here a telluride glass melt, which is cast into here a cylindrical brass mold. And at Optofab Adelaide, we have facilities for melting at ambient atmosphere and at controlled atmosphere. Another technology is chemical vapor deposition. This is used for making commercial silica fiber preforms from which then telecommunication fibers are made for the fiber optics cables that connect us through the internet. Another technique is the sol gel technique. This is used for making glass coatings. So now let's look at the fabrication for the two different fiber types. One is the solid core fiber, so solid core, solid cladding. The core glass has a higher index than the cladding glass, and therefore the light is trapped in the core region. Another type of fiber is the microstructured fiber. One type is shown here, so air holes are there's an air hole pattern, and in the center is a missing hole. And so what it means in this region, the refractive index is lower because of the air holes compared to the solid region. So therefore also the light is guided here in the solid core by a modified internal reflection, very similar to solid core fiber. So if you look at these fibers, then all these fibers are made from a preform with a microscopic structure. Here you see a preform with air holes. So on a research scale, how we make preforms, we have our preforms have 10 to 20 millimeter outer diameter. What is interesting, there are a range of technologies available to make such preforms. One is the chemical vapor deposition, which is used commercially. Another technology I mentioned already is the casting, which is also used commercially for making specialty fibers. Then other specialty techniques are the extrusion technique, ultrasonic machining, stacking, and also recently 3D glass printing has come up. And there are a few other more exotic technologies to make a preform structure. Interestingly, all research groups who are doing preform fiber drawing, in the end then they take preforms and have a draw tower, and then the preform is stretched on the draw tower down to fiber. So now I go through a few of the preform fabrication techniques. I mentioned the glass melt casting technique. This is what we use at Optofab Adelaide. And recently for the special Zeblan fluoride glass, which was indeed then drawn in space, I talk about this later on, we use the rotational casting to make the preforms. So it works, we need a cladding glass and we need a core glass. I need to move us a little bit around if I can do this. No, it doesn't work. So we start with, we put cladding and core glass on top of each other in the furnace. Cladding glass on top so that it can be first cast into a tall, rod-shaped mold. We only fill it roughly half of the mold. Then the mold goes into a lathe, is spun in horizontal direction, and therefore we then form a tube. Then the mold is put back in the vertical direction and the core glass is cast into it. So we make the core glass preform in one go during the melting and casting. Another technology is to make a solid glass billet. Let's see what I have here. Yeah, for example, solid glass billet. Place it on top of a metallic structure, a so-called extrusion die, and then heat up the glass and die, and then squeeze the glass through. And so where is the pin that blocks the glass flow? There is then a hole in the extruded preform. So the extruded preform has always the inverse structure of the glass, of the metal die. And what you can then see here, really a large varieties of structures can be made with this extrusion technology, and we have used it for a broad range of polymers and glasses, for an almost unlimited range of structures. To make some of the exotic structures, we need really sophisticated die structures, and there we now use increasingly the 3D metal printer available at Optofab Adelaide. Another extrusion-based technique is 3D glass printing. And this really has come up in the last 4 to 5 years. We have a commercial 3D glass printer for Maple Glass Printing, a startup company in Melbourne. And you see here the glass is coming out of the hot nozzle, so thin glass strand, and then layer by layer the glass piece is built. We started to investigate the 3D glass printing from a glass art point of view, and so we made these various glass art pieces, but also then we looked into making a tube-shaped preform, which then we have also drawn to fiber. Another technology to make holes into a glass preform is to the drilling, the ultrasonic drilling and milling. And so we have our CNC available for this. It has an ultrasonic function so that via core drilling or via milling, then these structures are made into glass. And because of the ultrasonic function, the cutting tool is not cutting, rather grinding its way into glass. And this is a gentle way, and therefore a sort of a translucent surface is obtained. Of course, you can imagine with drilling and milling, very accurate structures can be achieved. But there's some limitation in the number of holes and the size of holes. So depending on glass type and applications, we use either the milling or we use the extrusion technique. Another technique which is used commercially is the stacking technique. It's a manual technique, but is the technology for making silica microstructured fiber preforms. And it takes silica tubes, silica rods. They are stretched to thin capillaries, thin rods, which then are stacked according to the pattern that is wanted. And one of the most complicated fibers made commercially in this way is the so-called kagome fiber. So we have had only small resources to work on the stacking, and therefore you can see here what we made in the past at Optofab Adelaide for a previous ARC Center of Excellence, but we really reinvigorated the stacking technology, and so please watch this space, because in the next year we want to do more process development on using the stacking for fiber fabrication. So I think I need to speed up. So fiber drawing is taking the preform and stretching it down to a fiber with in the order of 0.1 to 0.2 millimeter outer diameter. So we have two fiber draw towers for soft glass and for silica. Here you see a range of structures we made out of polymer, soft glasses and silica. Don't go into details because I want to use the little time I have left for a few applications. So one is the waveguide chip laser. I like this application because it was started really at the Macquarie node or Macquarie hub of the Optofab node via key people were Michael Whitford and also Dave Lancaster. Dave then moved to the University of South Australia. So this team, they started to work on making these waveguides into Zeblan glass, taking a femtosecond laser, so making very compact waveguides and therefore lasers. And they did this first with fluoride glass. This was then also commercialized by Dave Lancaster in the company called Redshift Photonics. And then Dave and I, we also had a PhD student together, and she extended from fluoride glass to germanate glass and making an ytterbium chip laser. Next example is work from my team developing an eco-friendly colored glass, which is a new versatile method to create gold and silver nanoparticles in glass. And these nanoparticles, they give the warm colors as shown here. By changing the glass type from germanate, silicate, and using gold or silver or alloys of them, a different range of glasses can be obtained. And that we worked together with Karen Cunningham from the Gem Factory at that time, a few years ago, when we worked with her, because we wanted to show that indeed our glasses are compatible with clear glass, and as you can see, she successfully made these glass pieces. Then what we looked into is the screen printing. So we not only made the wool colors, we also have, for example, cobalt ions in glass, which give then the blue color. So you can imagine if you mix blue with the yellow color, or you get green, and if you mix the blue then with the red color, you get another color. We also formed a startup company 3 years ago, and we are now looking into the commercialization of this technology. Just looking, I still have a few more minutes left. Another example is magnetic field sensing. Key point here is nitrogen vacancy centers in diamond. They have a fluorescence in the visible, in the red, and this fluorescence is sensitive to magnetic fields, and therefore, while you're looking at changes in this fluorescence, the magnetic field intensity can be inferred. And to get now the nanoparticles or the microparticles into a fiber, to use a fiber for the sensing, for example, for remote sensing applications, we took a thin glass rod, dip-coated it with diamond particles, placed it into a glass tube, this assembly drawn down to fiber, and you can see here, this is the fiber, that really in the fiber then we have embedded the particles so that they are now fixed in the fiber, so robust piece, or this is a method to embed the particles in a fiber itself, which then can be used for the sensing, and won't go into details how then the magnetic field sensing is done. A few slides now on another sensing applications using these suspended core fibers and exposed core fibers. So here you have the tiny core in the center surrounded by air holes. Light is guided in this small core. A portion of the light goes into the air holes and can be used then for sensing via light-matter interaction by filling the holes with material. And we can make these type of fibers with different core sizes, and also, as you can see here, with different hole sizes. So we really can adapt them to the target application. I want to give one application example where the holes are not filled with any material, but the holes are used to make a fiber where the light is guided in this core. So it's a single material fiber, pure silica, taking the femtosecond laser, a so-called grating is written into the surface of the fiber core. And again, because the grating is written via air holes, this is also a single material grating. And what it allows us then to go to higher temperature. So first, the grating means that when light is, broadband light is launched into the fiber, one looks at the reflected light, only one wavelength is back reflected. It's really given by the periodicity of this fiber brick grating and also the refractive index of the glass. Now, if now the temperature or pressure is increased, what it means is that the refractive index of the glass changes slightly, and this changes now the wavelengths of the back reflected beam. And so therefore monitoring the wavelengths of the back reflected light allows us now to do the temperature sensing, which is shown here. Because everything is single material, the fiber and the grating, we can go up to the silica deformation point, which is 1300 degrees Celsius, for short-term sensing, 1,200 for longer-term sensing. Several gratings can be written in one fiber, and this then allows multiplexing. Again, I would like to mention a startup company, HD Sensing, and they embedded this type of fiber sensing in a furnace that has been used for zinc smelter at the Port Pirie Nürster facility. The exposed core fiber, we have used it for collaboration with many university groups in the world. They use these fibers for testing new coatings for sensing, new concepts for sensing, also new concepts for new physics concepts, for example, high-index thin films and 2D semiconductor films. I won't go into detail of that. I want to use really the few minutes I have to my recent topic of developing the next generation of fiber optics cables. So, as you all know, we need submarine fiber optics cables to connect us, to connect the continents so that we can have the internet. Now, current fibers, they're made from silica, that means from sand. Every 100 kilometer, an amplifier is needed because the fiber, the light signal over the 100 kilometer decreases in intensity. So roughly, to go from Sydney to Los Angeles, we need 120 amplifiers. And these amplifiers need to be run with electrical energy. And so therefore, fiber optics cables is rather, you can say, an electrical cable to run these amplifiers. So there's really a driver to have less amplifiers so that we can have more signals going into one fiber. And theoretically, the so-called exotic Zeblon fiber allows to do this because theoretically it has a lower loss. What it means, the light only decreases over 2,000 kilometers to such an extent that only then an amplifier is needed. So theoretically, we would only need 6 amplifiers from Sydney to Los Angeles. Huge improvement. So very happy. Theoretically, practical, it's the other way around. So current Zeblon fibers, their loss is even worse than that of the current fiber optics cables made of silica, so we would need more amplifiers. So we need to do something that the Zeblon can achieve what it theoretically is able to achieve. So why is Zeblon not as good as it could be? 2 reasons. One, it has impurities in the glass, transition metal ions like iron or copper. And so I got the funding from the Australian Research Council to work on the purification of the glass raw materials here on Earth to get rid of iron, copper, and other contaminations in the raw materials. The other side of this story is the crystals in glass because they cause scattering. And what you can see here is obsidian, it's a volcanic glass, a natural glass, and over millions of years of times, then these snowflakes have formed their crystallite, crystalline, again, silicon dioxide has a white color. And this is not what we want to have in a glass because it causes scattering. So for avoiding the formation of these crystals, we draw glass fiber in space. And why in space? For the following reasons. So to grow a crystal, one needs to transport the atoms in a glass so that the crystal becomes larger and larger. As shown here, so gravity helps the mass transport via convection to grow the crystals. So therefore, if we want to prevent the growth of crystals. We need to get rid of gravity, and that means to draw fibers in microgravity. That means on the International Space Station. Now, let's put this into perspective. Here you see an industrial scale draw tower is 50 meters. Here you see 2 human beings on a draw tower. This is not the complete draw tower. This is only the upper part of a commercial draw tower. Now, to give you a perspective of our soft glass draw tower is 4 meters. And so you see me next to lower part of the draw tower. Now, even this draw tower, even if it's small compared to a 50-meter tower, is still far too big to put it on the International Space Station. So we have been working together with a company called Flawless Photonics, and they have built a miniature or a small draw tower or a drawing device. And this is so small, only 1 meter in height. If you put it on Earth in a vertical position, of course on the ISS you can put it in any direction because there is no gravity. And you see here the astronaut who put the preforms into this miniature drawing device. And so this is really to do the fiber drawing in space. A huge consortium is needed. So we made the rods and preforms for the space drawing. Flawless Photonics miniature draw tower. Institute in Poland, they made Ziblon rods for testing. International Space Station, national laboratories, then a lot of funding agencies. And so in January, then the draw tower, the fiber went up to the ISS with the SpaceX Falcon. Then these 2 astronauts and also another astronaut, they put the preform into the draw tower, and then in Luxembourg, Flawless Photonics company, they were driving the draw tower, and they made up to 11.9 kilometers of fibers via several fiber runs. The fiber has come down to Earth. I actually have seen the fiber, was there when they respooled it, and now a few research groups, we are looking into the characterization of the fibers. So watch this space, because hopefully we will be with these fibers one step closer to a bright future. Further acknowledgement, of course, many groups have been involved in the research I presented. We got the funding from many funding agencies and sponsors. Really special thanks to the Optofab Adelaide team. And as a summary, conclusions, various glass type, therefore many properties. Therefore, I've shown you a wide range of applications. I mentioned glass art, and therefore I would like to make you aware that the famous glass artist Chi-Hui, he will have an exhibition in the Botanic Garden from September this year to April next year. And IPAS and University of Adelaide, we took this opportunity, and we are currently working on having an exhibition showing glass science, the journey of light, and there will be also public lectures. There will be more information forthcoming, but I already wanted to give you the heads up. Thank you for your attention, and apology if I took a little bit longer than allocated.
Thank you, Heike. We did start you a little bit later, so no need for apologies. I think you're pretty close to where we want you to be. So what time is it there, Heike? Just remind us.
At 2:18 in the morning, so not too bad.
Right. So yesterday I told everybody that we've got some amazing volunteers and speakers who are very committed to Winter School. I think you're case in point for that. So thank you so much for staying up late to speak to us live. we gave Heike the option to record, but she wanted to speak to you live, which means that she's also got a chance to answer questions. So is there anyone who would like to ask a question either in the room or online? Belle's going to keep an eye online. In the room? Yes, question over here. You might just speak up. I think you should be able to hear you. Okay. Can you hear, Heike, can you hear the questioner?
No, Craig, if you don't mind, then to repeat it.
Okay.
I was just asking, it's kind of maybe a bit silly. When you were mentioning the stacking technique, you mentioned a fibre. I don't know if I misheard, called kaugummi, which is like chewing gum. I was just wondering why it was called this.
So the question is about the stacking approach to creating the fibres, Heike, and I think the question is, there's a kaugummi, did you mention, and what is this referring to?
Yeah, whether it means chewing gum. I was just wondering if it, unless I misheard, why it was called.
There's some reference to chewing gum in the question. Is that? Can you?
So it's really the structure that comes, I think, from Japanese, because this pattern is called kaugummi.
So it's a reference to Japanese, something Japanese. Okay. Thanks, Heike. Any more questions? Paul, yes?
I just have a simple question, gee-whiz question. What is the weight of 11.9 kilometers of optical fiber
Right.
down from the space station?
It's a great question. Heike, what's the weight of 11.9 kilometres of optical fibre and the transport back from space?
Yeah. This is roughly 10 to 12 preforms, and each weighs in the order of 50 grams, so it's only 500 grams. This is the nice thing with fibers, because they are lightweight.
Right.
So you can make very long fiber, and you don't need much kilogram for it.
Thanks,
You've got to
Heike.
work it out. It's 150 microns diameter, so...
Any questions? Anything online, Belle? Any more in the room? Chance for one quick one, if there's anything. Yes?
What's how the fiber drawing towers work?
Heike, can you briefly perhaps explain how the drawing fibers towers work?
So let me go quickly back. I can't hear. Yeah, any moment there. Because it's then easier to explain. So the preform, a short section of the long preform is heated up. The glass deforms. And therefore, if now a tension is put at this fiber, so first, here on Earth we are so lazy, so easy, gravity makes then the drop coming down. We remove the drop, and then the dangling fiber is put onto the drum, which then starts to rotate. So the preform goes slowly into the hot zone, via drum rotation fast out of the hot zone, and therefore from millimeter scale the glass is stretched down to the micrometer scale.
Okay. Is that the one I just see there?
Yes.
Yep. Okay, so there's one more question perhaps, Heike, from online. When drawing, it's disappeared. When drawing the fibre, what parameters are important in determining its properties?
So it's the drawdown ratio, which is the ratio between feed speed and draw speed. If there are holes in the fiber, then we can pressurize the preform to keep the holes open, or even to inflate the holes. The process control is done via this diameter gauge. And so then we can even have a feedback control loop, so that the drum rotation is adjusted so that the fiber diameter is maintained. So I think it's not many parameters, but they really have to be balanced in the right way to achieve the target structure.
Thank you very much. We're going to, I see a few more hands up. I'm sorry, we really have to move on, even though I'd love to keep the conversation going
And don't forget,
further.
questions will be answered at
Yeah, if you've got further questions on this topic, come to the Optofab tour tonight. Heike is, leading the group, but she's got some pretty amazing people working with her who'll be able to answer some additional questions. But can you all please cheer as loudly as you can so Heike can hear you? Thank you so much, Heike. We really do appreciate your support from the school and the amazing science you do, and we wish you the very best for your further travels. But the space research, we'll look forward to the next instalment of that. So best wishes for that. Thank you very much. Okay. So
Thanks, Craig, and thank you all. See you.
Thanks, Heike.
Bye.
So, excuse me. So we're going to move to our next speaker. I'm just going to see if I can do this seamlessly. Let's see. Where is it? Belle, what is the...
So it's on the desk drive. It's just here.
Not so simple.
All right. Is that? Have you shared? Yeah. Have you shared? Not yet. Can you just make sure you share?
Okay, we will...
Is this working?
It should be working.
Is there
Yeah.
a nice...
And I'll pin us. Yeah, just a minute. Just try clicking forward to that. Just try clicking forward and see if it's working. Yep, okay. Yep, go back. Okay, so our next speaker is Scott Foster from DSTG, and Scott's supported us for many years at the school, so thank you very much, Scott. We really appreciate it. And I have a feeling that every time I read the bio, it's out of date, so apologies, but I think the talk in a way will speak for itself. But Scott is an expert in the use of fibre technologies. You're going to see some amazing applications here, in this case for undersea sensing. It's a very interesting talk, and again, we appreciate your support, Scott, and it's great to have people of your calibre come and join us. So I will hand the mic to you. Thank you.
Thanks, Craig. So what I want to talk about today is I just want to give you a little bit of flavour for precision sensing, particularly in the context of defence applications, and specifically in the context of undersea warfare. And one of the things that I want to try to get across is at the heart at the heart of every exquisite sensor is an exquisite material, and that material science and materials processing is absolutely at the core of advanced sensor technology. So undersea warfare, unlike other warfare domains, like what they call the land domain, for example, you can't use radar or other electro-optic means in order to actually see things underwater. And so there are basically two kinds of sensors that we're interested in. We're interested in sensors that peer into the water column from above, and they could be laser-based sensors. And we're also interested in sensors which are actually deployed into the water column, which actually operate underwater. And it's those sensors that I'm going to talk about today. And in particular, what I'm going to talk about is acoustic sensors, or sonar. So sonar is basically the primary sensor for submarines, and also the primary sensor for detecting submarines, because you can't see underwater. Electromagnetic radiation such as radar doesn't propagate very far underwater, and so sonar is the longest range way of actually sensing your environment underwater. And the reason that sonar is an extraordinarily difficult field, and that the acoustic sensors that we use in sonar have to be very, very, very sensitive, is that submarines really don't want to be seen. And they're really, really good at hiding in the noise under the water. And so we need very, very sensitive devices in order to try to detect submarines at any kind of range of value. So the basic technology that underpins all of undersea acoustic sensing is what's called a hydrophone. So a hydrophone is just basically an underwater microphone effect, essentially. It's basically a device, usually an electrical device or electronic device, that responds to changes in water pressure. And so almost all hydrophones since the 1960s have been based on the piezoelectric effect. And so the piezoelectric effect is very simple. You take a material which is piezoelectric, and you apply pressure to that material, and the material has this interesting property that when it's deformed, it actually generates a charge, and you can detect that on a detector. So that's how piezoelectric hydrophones work. And when I say that piezoelectric sensors have dominated sonar since the 1960s, I can actually be more specific than that. It's actually one material, one remarkable material called PZT. And you've probably heard of PZT. What it actually stands for, it's used for in headphones, in microphones, in speakers. It's used in the starters for gas stoves and barbecues. It's a ubiquitous material in industry. But it's also pretty much underpins all of sonar technology. And it has this extraordinary property that it has what's called a morphotropic phase boundary. So it's a binary perovskite ceramic, which is essentially a mixture of lead zirconate and lead titanate. And both of those, in their native form, both of those species exist in a slightly different crystal orientation or crystal structure. And when you mix them in a ratio that's close to 50%, the material, in a sense, becomes unstable. And this instability, where it's not quite certain which crystal phase it wants to be in, and this is called a morphotropic phase boundary. And it's this particular material or thermodynamic property which is the basis of a phenomenon called giant piezoelectricity. And this is the exemplar for giant piezoelectricity, this material. So why do we need extraordinary materials in order to do sonar? So what I've just done here is I've just sort of summarised just some of the challenges of underwater acoustics. So the first thing, you require devices with a pressure sensitivity of about to be able to measure pressures of the order of 10 to the minus 9, 1 part in so 10 to the minus 9 atmospheres, in an environment where the background variations with depth can be up to 50 atmospheres as you go from sea level down to hundreds of metres in depth. So if you think of that in terms of a sort of a precision, you're talking about sort of 1 part in 10 to the 10, so better than 1 part in a billion. That's a very difficult challenge, and you need to do that over from about 10 hertz up to tens of kilohertz. So it's quite demanding that you need to go into quite low. You need to go down to quite low frequencies because that's where the sound propagates the furthest underwater. And you need to be able to do this in an environment which is electrically corrosive, electrically conductive, and biologically active. And in particular, these are exquisite electrical devices that we're throwing into seawater, into an electrically conductive medium. And so it's extraordinary that they actually work at all. And a sonar doesn't just consist of a single sensor, it actually consists of hundreds of sensors. So what makes a better hydrophone? So you might think it's just sensitivity. The more sensitivity, the better. And that's kind of true, but it's a bit more complicated than that. The real drivers for advances in... so hydrophones were already very, very sensitive, but they're actually quite big, quite bulky, and that constrains what we can do with them. And they're also electrical devices in a hostile environment. And so basically the drivers for advanced acoustic sensors is really driven by two things. Right, hotel load and availability. So hotel load is, so you can think of any kind of military platform as like a hotel, and all of the sensors on it are clients, all the systems on it are clients. So that's where the terminology hotel load comes from. The size, the weight, the power, that's the resources that the sensor actually takes from the system. And availability, so you need it to be available when you need it. So that's the reliability, the persistence, how long you can keep it out there. For example, if it's on batteries, as opposed to whether it's on a tether, for example, or on a platform, the cost. And obviously cost is always a big driver. So what you can see there on the right-hand side is actually an experimental fibre optic array that we developed at DSTG. I'm going to talk about that right at the very end of my talk. And given where we are, I might run out of time. But what I really want to talk about before I get there is I want to talk a little bit more about advanced piezoelectric materials. So another way of looking at this is just imagine that you want to sit down, you're an engineering team, and you want to sit down and you want to design a hydrophone or an array, a sonar array, and you need to select what sensing material or what mode of sensing you're going to use. And so what you might do is you might write down a whole bunch of what we call figures of merit. So obviously sensitivity is going to be a key one, but there are and cost is going to be a key one, which I've got at the bottom of the table, but weight is going to be important, size is going to be important, and there are a whole range of other considerations that you might want to think about. And so what I've got here, what I'm just showing here is basically just a table of 3 different approaches to hydrophone. So there's piezo-ceramic, which is your PZT. So that's your classic hydrophone. Single crystal piezoelectrics, which is what I'm going to talk about a little bit more in a minute. So these are new advanced materials, which in many respects are superior to traditional PZT. And it's something that we've got that we're very excited about, and we're doing. And then fibre optic, which I'll touch on at the end of this talk. And I've just colour-coded the advantages. And the point is there's no one perfect sensor, right? Depending on what you're trying to do, there are a whole range of different considerations. And so it is a bit of a wicked problem. You have to make choices, you have to make compromises. But sensitivity is really what I want to focus on. And as I've just alluded to in the previous slide, sensitivity is not just about sensitivity. A better way to say it would be the trade-off between sensitivity and size, right? Getting the sensitivity that you need in a size that your platform can accept. And so it's more complicated than just saying, oh yes. So what I want to talk about for the next few slides, and I'm going to go into a little bit of detail, is what we mean by sensitivity. But before I do that, I just want to explain what these single crystal piezoelectric materials are and how they're fundamentally different from PZT, which is a piezoelectric ceramic. So a ceramic is basically a polycrystalline material, and if you can see on the diagram on the right-hand side there, basically all of its different grains are all orientated differently, and it exhibits a bulk behaviour which is independent of the orientation of any one of those grains. Single crystal is simply where the entire bulk material is made up of just one crystal. And it turns out the PZT, you can't actually fabricate PZT in single crystal. At least not in large enough volumes to be useful for sonar. It shouldn't be surprising that the piezoelectric properties of single crystal materials are greater than the piezoelectric properties of polycrystalline materials. But what's only recently been able to be achieved is the development of new exotic engineered materials which actually have piezoelectric properties which are actually superior to PZT and which can be manufactured in single crystal. And what you can see there is right down in the bottom right-hand corner there is a crystal that we developed with a whole bunch of partners, which I've listed there, I'm going to see if I can pronounce it, PMNPT. So it's lead, manganese, niobate, lead titanate. So it's a ternary single crystal piezoelectric material, and this is the first bulk single crystal billet of this material that was fabricated in Australia, and just only about 2 or 3 years ago. And this was grown using the Bridgman process, and there are a couple of different processes that can be used to make these materials. Right. Okay. So what I want to do in order to explain what makes it more sense, I want to spend a few slides. I'm going to show a few equations on these next few slides, but don't panic. There won't be a test afterwards, and hopefully you can get the gist of what I'm saying just by listening to the words and looking at the pictures. So the way in which a piezoelectric hydrophone works is it's basically a capacitor. So it's basically a capacitor where the piezoelectric material is the dielectric. And what happens is that essentially you have a polarization vector inside that material, and let's see if this works, when stress is applied to the material, it deforms the material, and it rotates that polarization vector and perturbs that polarization vector. And that actually causes an electric displacement which leads to a charge separation which is registered on a detector. And the way in which the piezoelectric material is described mathematically is through a set of thermodynamic state equations called the constitutive relations. And that's these equations that you can see here. I'll just see if I can do it on the other side as well, these here. And what they do is they relate basically the stress, the strain, the electric field, and this thing called the electric displacement. So the electric displacement, if you don't know what it is, it's basically just the charge per unit area that collects on the surface of the material, right? And the important point to see here is that essentially what happens is that you have something called a piezoelectric coupling, which means that the stress and the electric displacement, i.e. the charge, are actually coupled by this materials parameter called the piezoelectric coefficient. And if you actually work out the voltage that's actually generated there, you can basically work out that the voltage, the maximum possible voltage that you get is related to this coefficient, of course, which is the piezoelectric coupling and the electric permittivity for a given stress. The voltage isn't actually a very robust measure of how sensitive a material is. What we're really interested in is actually the maximum energy that can be extracted from the acoustic field per unit volume of sensor material. And it turns out that when you actually work that out, just using the relationship between voltage and energy, when you actually work that out, what you find is that the maximum energy that can be extracted from the acoustic field, that is what's applying the stress per unit volume of sensing material, is actually a material figure of merit. It actually depends only on the properties of the piezoelectric material. And it's this quantity here, which is the square of the piezoelectric coefficient divided by the electric permittivity. Don't worry about that. We just call it the figure of merit. So what that's saying is the higher that figure of merit for a particular material, remember it's a property of the material, it's not a property of the device, right? Then all things being equal, you can extract more energy from the field with a smaller, the same amount of energy from the field for a small amount, smaller volume of material. And if you actually look at this figure of merit for a whole bunch of materials, what you find is that these new emerging advanced materials like PMNPT and another one called PIN-PMNPT, which I won't even try to actually spell that. The I is Indian, if you're wondering. And the P is always lead. So these are all lead-based materials. They're all lead oxides of some description. But you can see that they're figures of merit in terms of the maximum energy that they can extract from the field per unit volume is an order of magnitude higher than PZT. So what that means is that we expect to be able to make devices that are much smaller and much lighter, remembering that lead is particularly heavy material. But that's not quite the full story. That's not quite what we mean by sensitivity. And the reason is because sensitivity is not so much about how much energy you can extract from the field, it's about how much information you can extract from the field. And in order to understand how much information you can extract from the field, you need to understand what the noise is, what's the minimal amount of energy, if you like, that you can extract from the field. So it turns out that when you rotate these polarization vectors inside the material, you generate a little bit of heat. There's friction, right? And that friction, because it's a thermal effect, whenever you have friction, you have what's called fluctuations, thermodynamic fluctuations, and those thermodynamic fluctuations cause voltage fluctuations even when there's no pressure acting on the sensor. And so those voltage fluctuations, they actually set a limit, right, on the minimum voltage that can be measured. It's actually the minimum energy. You can see that's proportional to V squared. So it's actually the minimum energy that can be measured. And when you take that and you divide that, or when you take that minimum energy that can be measured and you divide that by the energy per unit per unit stress that you can achieve, what you actually get is you get a measure of effectively your noise floor or your sensitivity. And that's what we call sensitivity. So that is the minimum amount of stress that it can actually be extracted by that material per unit volume, per unit field. And so we get this new figure of merit, which actually has a new parameter in it, which is called the dielectric loss, which is the heat generated or the friction of the material. And again, this is entirely a material property. So this is the minimum measurable stress per unit volume of sensing material. So when you put all this together, what you can do is you can actually calculate, because if you actually have a look at this formula here for the noise floor, it actually depends on frequency. So what I'm actually showing here in this plot here is a plot for a whole different bunch of materials of what's called the noise equivalent pressure per unit per cubic millimetre of sensor material for a hydrophone with unit gain. Don't worry about the gain, I don't have time to explain what that is. It's basically the amount of extra area that you use to gather in the force of the external field, right? The point is that if you have a look at this, what this is telling you is that the amount of pressure that you need to exceed the noise for a ceramic hydrophone is much higher than the amount of pressure that you need to exceed the noise for a single crystal hydrophone. So these can actually measure much smaller, for the same amount of material, these materials can measure much smaller pressures. And if you have a look at the list of various materials there, and you have a look at what these figure of merits look like, we're actually talking about not just a factor of 10 difference, but a factor of 100 difference between conventional standard PZT materials and these advanced materials. But you'll notice that blue curve at the bottom. So that blue curve at the bottom is actually an equivalent curve for a fibre optic hydrophone. So what's that all about? Well, there's more than one way to skin a cat, as they say. So I just want to come back to this fibre optic sensor that I showed earlier in the presentation. So each of those silver blobs on that picture on the right-hand side there is a fibre optic hydrophone, and inside that is something called a distributed feedback fibre laser. So this is a sensor that works on a completely different principle, absolutely, totally different principle. So what it is basically a very small amount of erbium-doped fibre. So it's an active fibre. It's a fused silica fibre that's been doped with a rare earth called erbium. And what's been fabricated in there is a fibre Bragg grating. A fibre Bragg grating, and a fibre Bragg grating is basically a device which is holographically written into the fibre using intense UV light. Our lasers at the moment are fabricated by ANFF in Sydney, who have that capability to be able to do that. And when you can fabricate these devices inside optical fibres, you can do things like you can build mirrors inside fibres, and that's what these fibre Bragg gratings do. In fact, they actually create something called an optical cavity. An optical cavity is a region of space where light is trapped. And when light is trapped in an optical cavity, when light is trapped in an optical cavity, then you get a resonance. And it turns out that with these erbium ions amplify the light once they're energised. I won't go into that. But it turns out that the only wavelength at which the laser will actually laze and produce light is at the exact wavelength which is a harmonic of that optical cavity. And when you strain that device or deform it in any way, then that changes the length of the cavity and that changes the frequency of the laser. And so what that means is by measuring changes in the colour of laser light down an optical fibre, we can measure extraordinarily small deformations of this optical fibre. In fact, we could actually measure deformations of the order of a femtometre, so that's about the diameter of an electron, 10 to the minus 15 metres, and that's small. And so these are some devices that we've fabricated over the years, again with support from ANFF, based on silicon microengineering techniques. I'm just going to, we'll see whether this works.
Hello, my name is Jonathan Hedger. I'm an APR intern currently working in the Undersea Sensor Science Lab, and today is the 17th of December 2020, and we've made this recording to demonstrate passive interrogation of a fibre laser hydrophone at the end of 100 kilometres of single-mode optical fibre.
Okay. So what you're listening to is tiny changes in the... What you're listening to is tiny changes in the frequency... Well, information that's extracted from tiny changes in the colour of a laser that's been transmitted down 100 kilometres of fibre. So these are extraordinarily these are extraordinarily sensitive devices. So what's actually going on there is the pressure is acting on a little beam. The laser is actually bonded to that beam. When the beam bends, due to the action of the acoustic pressure, that actually stretches it a little bit. And what you can hear is Jonathan's chatter. at the other end of the fibre. I won't explain how we actually demodulate the information off of that frequency in order to actually generate sound that you can listen to. But it's a little bit like demodulation in the RF. It's just that the carrier is light rather than a radio frequency. So it's a little bit like an optical radio, if you like. Okay, so I'm just going to finish. I'm just going to finish with a lazy Thursday afternoon at the bottom of the Gulf St Vincent. If I had more time, I'd explain what it is. Okay, what you're hearing is our trials vessel, which is about half a kilometre away, and the second, the capital engines. Okay, can you hear that crackling? Does anyone want to guess what that is? Did someone say shrimp? Okay, correct. It's prawns. Okay. I find that just such a peaceful such a peaceful sound. So that was an array of 8 hydrophones. So what you're listening to is a single hydrophone. So that's sitting on the bottom in about 40 metres of water in the middle of the Gulf. And there it is. I think that's it.
Thank you very much, Scott. There's nothing more peaceful than an experiment working perfectly.
It wasn't so peaceful half an hour before that recording was taken.
Are there questions for Scott? We don't have time, but we will do it anyway. So questions? Yes?
Thank you, Dr. Scott. My question is, will the constant stress-de-stress cycle affect the crystal lattice of the piezoelectric material over time?
Okay. Sorry, could
Maybe just repeat the question.
Repeat the question just slow.
Stress-de-stress
Yep.
cycle of
Yep.
the piezoelectric material
Yes.
affect the crystal lattice.
So the actual stress cycle of the acoustics is not so. That's only a very small perturbation. So we expect it to be quite stable under multiple cycles. What's more of a concern is the pressure cycling. So, for example, if say you have a sensor that's mounted to an underwater vehicle of some kind, and it's going down to 100 metres. So 100 metres depth is so it's basically 1 atmosphere every 10 metres. So 100 metres depth is 10 atmospheres of pressure. If you're going down several hundred metres, you can do the maths, right? And so going down and coming up again, so that deforms the material. That physically deforms it macroscopically. And so the pressure cycling under that macroscopic deformation is something that really needs to be, that's a really important characterisation that has to be done if you're going to qualify one of these sensors for example, for military use. The other thing that I'd say about nothing comes for free, right? So one of the reasons that PZT, I emphasise the fact that PZT had exquisite sensitivity, which it does, but another reason that makes PZT really, really useful material is that it's a ceramic. Ceramics are cheap to make. They're very, very flexible in terms of how you can make them into any shape you want, and they're extraordinarily robust. They're very, very hard. And that's a really good thing because there's a lot of pressure. There's a lot of pressure underwater, and really, really hard materials is what you want. So these more exotic materials, they're soft and they're brittle and they're fragile, and so that's one of the things that one of the challenges that we have in sort of developing useful devices is developing processing techniques in order to reliably and robustly machine these materials, for example. And also, one of our threads of research is exactly what you were talking about, trying to really understand how these materials behave under extreme sort of pressure cycling, and also electric field cycling, so voltage cycling, because they're also used as underwater speakers as well as transducers.
Yeah, we'll have one last question and then we'll go to morning tea.
For your sonar, so how deep kind of sonar detect? If we for the practical reason, so probably detect it submarine.
So that's an engineering. That's an engineering question, and it's what I mean by that is I don't mean that like as in that's not interesting. What I mean is that it's very specific to what you're trying to do. So there exist undersea vehicles that go down to the deep ocean floor for oceanography, for example. So if you want to equip one of those, if you want to equip a UUV for oceanography. To go down to the bottom of the Challenger Deep, then you need to operate. That sonar has to operate at 5-10 kilometres. On the other hand, if you just want to surveil littoral, say for a military, if you want to just monitor traffic moving through a port, for example, then it's only tens of metres. So it's really obviously the deeper you go, the more challenging it is.
All right. Well, thank you very much, Scott. We're going to morning tea. I think, are you going to have a coffee with us briefly? Yeah, excellent. So Scott will be around for... Scott's dying for a coffee. So if you also are dying for a coffee, grab Scott and you can drink coffee together and ask questions. But we have a gift for you, Scott. Thank you very much. We really appreciate your support over many years. It's a wonderful talk. You've got great knowledge in the field, and I'm sure there'll be many questions and great discussion at morning tea. So thanks again. Belle, I might do the video now, and then we can go. It's 3 minutes. Yep. Okay. So I'm just going to quickly jump out, hopefully, and into this very briefly. But I needed to share first. You'll get morning tea in just a minute, everybody. I promise. Okay, we're just going to see a short video from our sponsor, and then you can get some morning tea.
The Olympus STM-7 microscope is designed for high-accuracy metrology and precise measurements in material science. With a basic configuration, often known as a toolmaker's microscope, an operator can quickly take measurements to see variations in production or tooling wear. STM-7 measuring software can be added, enabling operators to take complex measurements, create testing routines, and efficiently deliver pass-fail results for components such as printed circuit boards and wafers. The STM-7 has a modular design. Customization for sample size, lighting, and motorization can be addressed by a wide variety of available options. In a toolmaker's configuration, operators simply place their sample on the STM-7 stage and locate the feature they wish to measure. Moving across the feature to an end point, the display shows the distance measured in all 3 axes. Olympus offers software to enhance the microscope's measuring capabilities. Using the software's edge detection function can simplify and speed up measurements. In this example, the software detects 5 points, while the user quickly moves around the sides of the rectangle and obtains results. Additional edge detection tools are available, including circle edge detection, which provides up to 99 data points for better measurement accuracy. Manufacturers often create hundreds of components an hour. Periodic sample testing must be regularly performed to ensure quality. The software guides users to each measurement point to ensure the correct measurements are taken. The software compares measurement results to known design tolerances and automatically displays any failure in red, so users know immediately if there is an issue. Stages for the STM-7 range from 50 by 50 to 300 by 300 millimeters and support objects as large as a 12-inch wafer or a component weighing up to 30 pounds. Stages can be equipped with a rotatable stage plate to simplify measuring in a single axis. By utilizing the clutch feature, the stage can be moved quickly for greater distance measurements. The STM-7 offers both manual and motorized height measurement. To improve reproducibility, a focus navigator can be added to the system. With a motorized frame, a convenient hand switch controls all height movement, while the Z-limit option keeps the objective lens from hitting the sample. A laser autofocus can be paired with the motorized frame. While moving across the sample in the X or Y axis, the laser autofocus controls the motorized height to keep the sample in focus. Integrated LED lighting supports controls for bright field or dark field reflected light observation, transmitted light observation, and the focus navigator option. For highly reflective surfaces, users can add a polarizer and rotatable analyzer. Adding a DIC prism improves the visibility of minor surface changes. The Olympus STM-7 measuring microscope is a versatile, high-performance instrument which provides operators three-dimensional measurements with sub-micron precision. Olympus application specialists and service engineers are available to conduct user training and provide industry-traceable calibrations. For more information on Olympus industrial microscope solutions, contact your local representative or visit our website at www.olympus-ims.com.
Great. Okay. So thank you to our sponsor. Morning tea is ready for you. Can I ask that we're going to try and come back in 15 minutes, so at was it 10:45, which is going to make it short. So please be brief with your. Okay, thanks everybody for coming back promptly. We'll keep going, hopefully make up a little bit of time before lunch so you can get to your tours on time. I think I've mentioned before how the different unit operations fit together. One of them was etching, and etching is very important in a lot of applications. And so we've asked Dr. Mike Pye from ANFF-SA here at UniSA to come and speak to you about etching capabilities. You will get to know Mike in the clean room. He's also doing one of the practical sessions, and so you can also ask him questions there. But just a little background, Mike has a background in microfluidic design and micro nanofabrication and extensive experience in manufacturing and product development. He's focused on the development of multiplex biosensing, a multiplex biosensing method, and he received his PhD in engineering in 2014 from the University of South Australia here. He joined ANFF-SA in 2015 as a nanofabrication technologist. He's experienced in many micro and nanofabrication methods, and that's a bit of an understatement. He's an expert in our clean room. He's experienced on pretty much all of those capabilities. And so if you've got any questions, not only about etching, but about photolithography or other areas, please feel free to ask him. So Mike, please come up, and we're looking forward to hearing from you.
Today I'm talking about etching. So etching is very important in microfabrication. Yesterday we had a talk about lithography, which is you map out where you want to start the process. And then carry on, you can do buffering. It's also covered by whole yesterday. Then today I'm talking about etching. So in my talk I will start from introduce what's the etching and how the mechanism is working, and I'm going to cover wet etching and dry etching. So I normally call dry etching because it doesn't use the liquid.
Sorry, I don't think we're sharing. I think we're good now.
Okay. Right. Then. So in the end of the slide, I'm going to cover some of nowadays application of the etching in the chip manufacturing. So
Just click on the screen. Yep.
all right, go. Started. What's the etching? Basically, it's remove the material, right? So we have, like yesterday, can form different features. You can like form the cone drive, micro needles, micro lenses, or micro fluid chains. There are so many publications of research use that these features basically you create a feature and rely on the property of these features to do the research or to do the application. Oh, can't quite hear me. All right. So maybe I stand here. Yeah, okay. All right. Then I come back to that etching mechanism. As I mentioned, there's two methods. First is use chemical etching. So you basically, you put all the chemical into the media. So media normally we use is water, or some chemicals we use in solvents. So use solvents or use water, basically is a liquid base. Then you use that and to rely on the reaction happen with your substrate. After that reaction finish, it remove the substrate. A second thing is the physical etching. So basically you will generate ion in the electric field, and then with that you accelerate the ion to bombard your substrate. Based on that bombarded, you remove the material from your substrate. So these are the two main mechanisms in etching. So wet etching, or we'll call dry etching, or RIE is a reactive ion etching. So etching type, first is the liquid with the wet etching, the gas using in the RIE, and then in wet etching, basically is a chemical base. Then the RIE included chemical and physical. And then the product finish is the waste in wet etching is the solution. And in RIE, you finish it, you come up with that gas, but you need to process lost gas. And then comes to the etching profile. For wet etching is isotopic, and then I'll explain later. And then RE come out is anisotropic. So the biggest difference between them is if you look at the features, cross-section features. So with the wet etching, you got the curved edges. And if you have using the dry etching, you will come up with the vertical sidewall. This is the biggest difference between those two. And I will start to cover the wet etching. So wet etching, basically, it needs that specific etching. That's why I say it relies on the chemical reaction to remove the substrate. Also, the second thing you need to consider is how you manage your waste, because it's contain the chemicals and also the substrate. And then you need to think about how to environmental friendly to process it. So in this wet etching method, massively using in the PCB industry, because it's batch process and you can easily process more than 20 pieces sample at the same time. Also, it's easy because just like I said, you use etching, put your samples in, and remove the material. Also, comes to here with that isotopic nature. The problem is the wet etching, you can't do very high resolution features. I can explain in the next slides. And then also it can use it for this kind of suspended structure. So which means you rely on the wet etching to remove the substrate underneath, and you have that suspended features on the top. So this is one of the methods we use to create this type of suspended features, like we have some micro there is a suspension can do like this. So next slide, I'm talking about isotropic etching profile. So this is one of the feature we form. The dimension of depth is, width of the channel is 70 micron, and the depth is 20 micron. So the left side is how we pattern it. before etching, we will pattern in 30 micron opening. And then we start to etch, use the chemical, remove the substrate. Because it's isotropic, so it will etch down 20 micron. At the same time, your left side and right side will be etched another 20. So totally, so I open step 30, it will be etched, and the extra 40, left side and right side, 20 micron on left side and right side. So when you add them up, it's 70 micron. So that's how that wet etching goes. Then next, I will jump to RE. The system we have, the dry etching system, is from OVAC. And then the RE, just like I say, it's rely on both chemical and physical. So I will cover more in the following slides. And so it involves the plasma etching. So it's a chemical reaction of a neutral. And then next one is the RE. So RE is you have that chemical reaction with the material, with your substrate to remove. And also you have iron to bombard your substrate. So it's commonly used, even nowadays, like chip manufacturers still using this method in their fabrication process. And then, but I point the last is expensive equipment, and also it's expensive to maintain. And the reason behind that is when you etch in different products or substrate, you will have byproducts happen in your chambers. Although, especially you have some involved the metal, it will become we call byproduct in your chamber, and then it will affect your etch rate. It turns out at a certain time you need to open the chamber, clean up the chamber, make sure the efficiency can go back to normal. So that's why we have a regular maintenance schedule for our etching system. It's the same for the chip manufacturer. I'm going to show you a video. How etching RE goes. Okay. So quick jumps. So from that video, you can easily see you ionize the gas, then gas has been ionized and bombarded to your substrate. Now the first slide, you finish your pattern masking with the photoresist, then the opening area will start being react with this gas and being removed. So inside that chamber, when doing the we call RE etching, it will have three phenomena happen at the same time. First is excitation, second is ionization, third one is dissociation. So these three processes running at the same time, and loss collisions happen and make the etching happen. So in the chamber, in a RE chamber, we have vacuum chamber, definitely, because just like the sputter, when you do this type of gas process, we want to have a good high vacuum chamber, which help the ion to move and more efficiently. And also we have the bias RF power, which to help us to ionize the process gas. Also, we can rely on that electro field to guide the ion to bombard the direction. So it doesn't bounce in anywhere. It just bouncing based on the electric field I gave. Right. So during the RE, two approaches happen at the same time. First is the vertical direction I am bombarded. Especially, like I say, we have the electrical field to control, and then we rely that the reaction of the iron with the substrate. I put silicon here with the fluoride. This, with that dry, we call RE etching, there's a different type of process gas. So in here, I use silicon as an example. The silicon and the fluoride, it will form that the silicon fluoride. Sorry, I'm not really good at that, but tetrafluoride, silicon tetrafluoride gas, byproduct come out, and then it will be removed after during the process. So also we have that sidewall with the passivation gas, so that's why it doesn't really attack the sidewall. And here the next slide is, because I say during the RE process, it combines chemical and physical. So in here, if you only have the fluoride gas on the left side here, actually the etch rate is quite low. Then if you only have argon iron to bombard your surface, it's more like physical. And then also the etching rate is also low. Only when you have mixing two processes at the same time, you can come up with a higher etch rate. So that's why if you say, I just need a physical, actually the efficiency is quite low, or individual chemical is also very low. You need to rely on both working at the same time. So here is another picture showing, because in our node, we are only processing the silicon substrate. We also can do silica substrate, so it's a silicon dioxide. Also, borrow for glasses, because it's a little bit different here, because for the borrow and the silicon, it's more involved in the physical. So we use ion bombarded to do the etching instead of chemical reactions. So it's a little bit different to the previous. Previous is like more about the silicon. And here is more about the glass. So back to the RE, then they come up to a deep RE, so-called deep reactive ion etching. So we call this process Bosch process. Yes, it's manufactured by that German Bosch, the company, and then we call it Bosch process. So it's a consistent etching process. Basically, you etch, the first step you etch your substrate, then you passivate the etching area with the carbon tetrafluoride gas. Then you carry on the third etching. So repeat that process, you can form the deep groove. Then I'll show you the video. So it's a repeat process. Okay, so in the final here, you can see we will form this kind of scallop structure on the side wall. And then after that, we can do some etching process to make the wall more smoothly. But this type of, we can verify the etching quality by this scallop depth and the scallop length to tell how about my etching goes, how's the efficiency goes. So if you look at that profile, you can go with that high aspect ratio That's the advantage of the RE process. And also you can come out with very uniform, and then increase the aspect ratio, and then both affected. And then once you decrease the etch rate with the time, that means when you go further deeper and deeper and deeper, but the process gas will be hard to reach the surface. Like I say, it's etching. You etching, you passivate, you etching, you passivate. When you go digging deeper, then you will find out that gas will be hard to reach to the bottom. So it will have a limit. But, okay, let's jump to the next. There's the current using. I get it from TSMC. Has anyone heard it? Chip manufacturer? Yes. Taiwan Semiconductor Manufacturing Company. Yes. I'm from Taiwan. I use this one. This is called co-op packaging. If now they're using, you might see it from somewhere for Tech 2. And yeah, so I can't stand out. I have to stand here. Okay. So why is it popular now? Because AI. The AI need that, we call it high performance computing. And then you might wondering why is etching coming from? And it comes from that. If you look at TSV, can you see TSV here? So it's called, full name called through silicon via. So basically using the etching process, like I'm showing you deep silicon etching process, you create that through hole. So that's called through silicon via. And then they using this type of interposer. So currently mainly is a silicon. They forming the hole diameter probably around 25 to 80 micron, and the thickness of that interposer is 200 to 400 micrometers. So if you see me, we doing some practical in the clean room. The standard silicon wafer we using is 525 micrometers. So basically, it's quite easy to form that structure. Even we have made this structure here with our previous process. So why is it popular? Because when you go with the high performance computing, you need to stack up the chips into a small devices. So it comes up with the idea to put everything into that interposer. So they stack them up. So now it's 2.5D packaging. So inside that interposer that's connected the chips. So basically you create a highway for the chip and memory communicate, or the signal runs through this processor and go down to substrate. So substrate with like the normal PCB board, then you can basically compact them into a small area. In the future, they go to this 3D IC packaging, so which means they will stack up more and then put more chips in one small devices. That helps that the performance of the computing. So that's currently using. And also the TSV, like I say, is formed by the etching process, dry etching process. Also on this HBM, high bandwidth memory. So currently high bandwidth memory, the manufacturers, 3 companies, mainly dominated by SK Hynix from Korea, Samsung Electronics from Korea, and Micron from US. So they are in the racing to make these high bandwidth memories. But the concept is quite straightforward. Is all the memory die, they stack up, and then with this TSV groove. Basically, they stack them up and create a highway for them that are signal to processing. So that's the currently using in the modern technologies. So this is the manufacturing process, how to make high bandwidth memories. Do I have time to go through it? Okay. So if you're working in a design company, that's the process design. So that's what you try to do. You try to map out everything you need to do. So I start with this gray one. So first you need to form TSV. Next one you need to do bumping. After that you do thinning. Then you stack them up. Okay, so first silicon etching. I think I talked this in previous slide. We rely on the chemical and the physical reaction to form that deep trench or deep groove. Then we fill it with the copper because copper is the main conductive material using. It's also a lot of research here because when you fill in the copper, you need to make sure the uniformity. That means when you create a highway, you need to put a good paving, right? Then the electron can move smoothly and quickly without the losing. Then after you do CMP, so CMP is the polishing process. It's mixing of chemical and mechanical polishing. So chemical, mechanical polishing. You polish in the copper, and then you start to form bumping. Bumping is helping that you do a contact pad. So these are the process to form the contact pad. Then you do thinning. You flip it. You flip it over, put on the carrier wafer. You start to polish in the top. And then you review that the TSV, the deep groove. So that's why they flip over to finish the polish in the top layer to thin it, also by CMP process. Then you have that contact come out. As you come out, you also have to do that bumping to contact. So more like the beginning of the roll and the end of the roll. Then you start to do stacking. You help them to align and stacking up. And then in the end, you finish the process, you form that high bandwidth memory. So currently, high bandwidth memory, the yield is pretty low. It using, for those three companies, they're good at manufacturing DDR5 memory. If you are a tech geek, if you don't know, you say it's the DDR5 memory. So DDR5 memory, the yield rate probably like 70, 90%, depends on the different company. But for high bandwidth memory, the yield is only 50%. But they still put a resource to make it because that's what demanded from. They want AI, they need a high bandwidth memory, so they need to do that HBM. Okay, what's next? TGV. So we have through glass via, this calls through glass via. It was announced by last year, September, by Intel. They want to, the next step, they're going to change the silicon to a glass. The reason behind that is they found out the silicon have defect. The silicon defect is because once you heat up the silicon, because you stack up a lot of chips on the top of the interposer, when they fully running, it generates a heat. And the heat will let the signal loss. It turns out the Intel changed the idea. They try to use that glass to replace. So that's why I say, in one of my slides, glass can be etched with IE as well. But the difference is, instead of chemical and physical, like onto the silicon etching, glass is more about physical etching. Okay, so that's the current modern process. And then also, it's quite interesting when I do in slides, actually, when they do etching of the glass, they beginning start with the RE, but as time goes on, and it's more about packaging, and they, like this gentleman holding this, it's a big glass interposer, or they call panel. Actually, they start to using laser to help to form this tiny hole. So later you will find out more from Ben's talk about laser milling. So this is my talk today. Thanks so much.
Thank you very much, Mike. Are there any questions for Mike about etching? Yes.
About this last slide, so as you mentioned that Intel is thinking to replace silicon with glass.
It's already going on. It's not thinking.
Yeah.
Yes.
So one of the reasons silicon is there because it's semiconductor property.
Yes, because once you heat up, that the loss will increase.
So how that conductivity can be introduced in the glass?
Oh, it's the same. Remember we say they have to fill the copper. They fill the copper with that the channel, the hole. So they use the same process. The difference is they change the silicon to glass. So that's what they currently doing. Yeah, in their packaging.
A couple of questions there. So the reactive ion etching, that's what they use for making flash memory when they stack them together?
Yes. Basically, it's a little bit different. But fresh memory is about the coating. So the coating, the coating material they apply is a little bit different. But fresh memory, they also some like industry they start to try to replace that HBM with the fresh memory, but still going. It's not ready yet because fresh memory needs to have the controller. Yeah.
And the second question, so if they're going to use glass as the
interposer.
Yeah, and substrate for this one, how do they deposit the silicon? Because they still need a N and a P.
No, actually, for the chip on the top, they still using silicon base.
Okay.
But the bottom, that's the interposer. Because in the future, what I can see the trend now, packaging is more important. Of course, they keep going, say they're going to scale down to 3 nanometers. Now it's 3 nanometers. Going to scale down to 1.8. Intel say they're going to be 1.4. But what's next? You can't go 3 more. It turns out they stack them up with that interposer. Because interposer, they need to, you have the interposer, it's like you build in an apartment, a high-rise apartment. Then you put more units in one floor, another floor, then you stack them up. That's why you need to have a good interposer as a carrier.
So one more question then.
Yes.
I believe there's efforts to make 3D monolithic chips as well, where they're using carbon nanotubes that they use large interfaces.
Yeah.
At the moment they can't do that with silicon, I believe it's because it gets too hot and it destroys the structures below. So why can't they just make like silicon functions, interconnects, and then more silicon, and then interconnecting more silicon?
It's more about why it starts, because it's when the manufacturing kept going on, silicon still occupy the majority of the chip substrate. Because it's cheap, it also has semiconductor property. But as keep going on, they need to process more data. It's more thermal will generate. Basically, it's the thermal. Also, the loss of the electro signal. Because, like I say, with the temperature go up, the signal inside I should say, electro transform inside that material will start perform differently. And that's why they try to do doping to get a better result, or they will do some, or originally the design is an insulator, but when the temperature go up, the insulation get worse. So they have to do something else. That's why different materials start to involve into that manufacturing, or they start to adopt different material. So it really depends on the case or what you want to use.
Okay, I'm just going to keep us going because there's probably a lot more discussion around that topic. Mike, there's also a question online, so if you maybe jump into Zoom and type one out to them, that would be fantastic. So let's all thank Mike again for his presentation. Okay, as I mentioned before, our next speaker is from Macquarie University in New South Wales, come all the way over especially to speak to you. Dr. Ben Johnston is the facility manager of Optofab, which is one of the nodes. And as I mentioned before, the University of Adelaide has a hub for that node, and you heard from Heike already. So you can join all the dots in this network that we're part of. But it's a great pleasure to have Ben here in person. I think the last few have had to be online. So Ben got his Bachelor's of Technology in Optoelectronics in 2004 and a PhD in Physics from Macquarie University in 2008. Since 2002, Ben has assisted with the running of semi-commercial laser micromachining services offered by Macquarie University. These facilities and activities form part of the ANFF, as I mentioned, and Ben's role is to provide fabrication solutions for researchers and industry using applied laser technologies. And it's amazing what Ben has got involved in over the years, and I'm really looking forward to hearing again from you, Ben. Every time is fascinating, so please welcome Ben.
Thanks, Greg. It's great to be down in Adelaide in person on one of the colder days that Adelaide's woken up to. But by way of acknowledgement of country, I'd like to acknowledge that we're on Kaurna land here on Adelaide, and we had a great opportunity with a colleague of mine last night, Tony here, to go out just outside of Adelaide to the International Dark Sky Reserve out near Swan Reach. And it's a really unique place to be able to go to, given most of us are living in an urban environment now. So if anyone gets a chance to do it, I'd encourage you to go out on country and visit some of these beautiful places that are only an hour and a half or so outside of Adelaide. This is a 30-minute shot of star trails that we took just at Big Bang Reserve, and then also a shot through the Milky Way there that we were shooting last night with a little bit of cloud coming through. But it really is a beautiful part of the country to visit. So I'm coming from Macquarie University. To acknowledge that's the Macquarie campus sits on the Wadamaragal clan lands of the Darug Nation in Sydney. And what we do there, well, another snapshot of the Optofab node. You heard a little bit of this from Heike, but yes, we are across the 4 different university sites at the moment: Macquarie, University of Adelaide, some facilities at ANU, and some facilities coming on board from RMIT. And basically the theme of the Optofab node is to produce components for managing light, so optics, optical fibres, the sort of stuff you heard from Heike this morning, but also carry out fabrication techniques which use light, like laser machining, laser inscription and things like that. So that's the flavour of what we do. So you'll get a good look at the Optofab facilities in Adelaide with tonight's event. At ANU we host some precision optics, manufacturing and optical coatings. And at RMIT, what will be coming online there are lithium niobate and photonics type devices. So that's a little spread of what happens in the node. So I want to concentrate on laser machining. And basically it's a pretty simple process when you think about it. You take your laser, you usually want some motion control or some scanning devices to manipulate your beam and move it around. And sometimes you involve some other gases or chemicals to help the process along. So just to give a little overview of the sort of lasers that you usually see around your university workshops and things like that, people are probably familiar with these CO2 sort of flatbed cutters. These are lasers where the wavelength is 9 or 10 microns. You're essentially using the laser as a precise heat source to blow away the material. So the spot size of these lasers tends to be relatively large when we talk about microfabrication, sort of in the hundreds of microns. But then there's an alternative to this which is being sold all over the electronic shops online now, and that's blue diode lasers for hobbyists. Okay, people they've gotten really quite clever of stacking these diode modules to get 20 or 40 watts of blue diode light on target, and these are really neat toys. But one thing I would stress that if you get to play with these things in makerspaces or get one for home, be really careful of your eyes, okay? These guys are not toys, and a lot of them are sold open frame like this, okay? So on that note, I'd just like to take a moment to talk about laser safety. Nearly all the lasers that we're using when we're doing fabrication will be class 4 lasers, so they do represent quite a danger to your eyes, your skin, and things like that. For those of you that get to visit the labs on the fibre optic prac as part of the afternoon activities, you'll notice over there in the laser labs, you'll see things like this: danger, laser on. There'll be laser safety glasses around and things like that. So just keep in mind that lasers aren't toys, and when you do get access to them and start using them, especially in the university environment, there'll be risk assessments and PPE you need to be aware of when you're using them. So to keep talking about other lasers, right, these are the big boys of engineering, these types of systems. These are the kilowatt sort of metal cutting lasers, and this is not what I'm going to focus on today, but these have existed for a long time in industry, and they're really impressive machines to see running. Again, many kilowatts of power, but the pulses are quite long, and again, you're just using the laser essentially as a directed heat source to blow the material away. Another niche use of lasers which has become really popular in recent time is to use them to do 3D printing. Okay, so the little clip I have here is just a picture of a selective laser melting system running. This is printing in titanium at the moment. So you have a powder bed of titanium, and layer by layer, the laser will come along and melt those particles together. This is all done in like an argon environment, so stuff doesn't burn. But again, another neat use of long pulse or continuous wave lasers to melt materials together. Okay. But this is not quite the area that I want to talk about. We want to talk about machining features with very high quality at really sub-millimetre scales. And the sort of scales we're talking about are down here, sub-millimetres. So we're sort of talking about components which are on a sort of a 1-inch scale down to centimetre scale, down to components which are millimetre scale, and then right down to sort of real sort of micron features when we're talking about putting small holes in membranes and things like that. I show a picture there of sort of a 5-micron hole. That's sort of the comfort zone you get to with the basic sort of laser machining system, though if you're working with a high beam quality and focusing quite hard, you can get your features down much smaller, even to sub-micron resolutions when you're drilling small holes and the like. So this is the sort of length scale we're talking about. There are plenty of resources to learn more on this subject, and I just picked out a series of textbooks here from Springer. They're all very good, insightful books. The thing about laser processing is there's a lot of weird physics that goes on, and these are the sort of books that give you some insight of what might be going on and how you sort of tailor a process, or how you go about characterising a process when you're doing this sort of caper. Okay, so these are the sort of processes that can take place. First, your material has to absorb the light, clearly. That light is generally transferred as energy to the material, which can allow a number of different physical changes to happen. You can have melting, you can have evaporation, you can have displacement from shock, you can have a really interesting process called phase explosion occur. That's when the material changes state in a very explosive way. So it goes from solid to gaseous very quickly, and essentially gas needs to take up a lot more volume than the solid material does, and so the material ejects itself away from the surface. And then you have other things going on, like the plasma generation, shielding of the incoming laser light by that plasma. And when we get to really short pulses, we can have a phenomenon called coulombic explosion. This is when the laser comes in and strips the electrons out of the surface, so the electrons exceed the work function. You're left there with a bunch of positively charged ions, which will then coulombically repulse themselves out of the surface. And that is a phenomenon that we really want to exploit when we're talking about doing features which are very, very high quality, because we don't necessarily want some of the thermal stuff. Because when you do get thermal stuff going, you can get some ugly results like this. You can get molten craters, you can get rough edges, you can get a little bit, that top right one there, that's a plastic component. So yeah, you want to manage these processes to try and get the best as you can out of it. Laser processes are never going to compete with a beautiful chemical etch process like Mike showed us in the previous talk, but there are many applications where you do want to come in and use a laser. Okay, I've got two versions of this diagram. Most of the lasers we tend to want to use for microfabrication are now falling into what we call ultra-short pulse lasers, and that means that the duration of the light pulses is getting shorter and shorter and shorter as people develop the different lasers. And these are just a couple of very hand-wavy diagrams of why people want to do this. Once you have lasers which are nanosecond or microsecond long pulses, the laser pulse is long enough to transfer heat to the surrounding material. And that generally has bad effects on what you're trying to do. It creates cracking, it creates molten edges and things like that. Whereas if you can use a short pulse, which doesn't have, the pulse being extremely short, it won't transfer as much energy to surrounding materials, and you can start to ablate very well-defined features. And here's just another one with a bit more detail added to it. So when you go looking up ultra-short pulse laser processing around the internet, these are the sort of diagrams and hand-wavy arguments you will get. I have one example here showing that there are limitations to this, though. This is shooting silicon with a femtosecond laser. You see at low energy that the little shots that we're making, they're nice and smooth, but once we get to a certain energy, we do start to generate some molten droplets. So you can't always push this to very high energies and very high removal rates. You have to be mindful of what's going on. But just to give you some examples of what these features might look like when things do work well, I've got some glass, some steel, and some platinum here. These are materials you can machine with ultra-short pulse lasers and get nice smooth results. Sort of results which, they're not really nano features and they're not as smooth as you can get with chemical etching, but it can be very quick to machine parts like this, and you can address a very wide range of materials. So we don't just have to concentrate on silicon or glass, we can do precious metals, steels, silicones, that type of stuff. Okay, a quick slide about the technology, the lasers that are at the core of these processes these days. I'm not specifically picking a brand, this is just the lasers that we've upgraded to recently. There are several companies making these class of systems. Light Conversion is a company in Lithuania that's got a very good market share at the moment because they're building very robust lasers at quite good price points. You can see, though, that the average power of the lasers that I'm talking about, I'm still talking about 20 or 40 watt class lasers, right? And those little blue diodes I talked about, the hobby lasers, you can get those at 20 or 40 watts now as well, right? What we're talking there is the average power. The special thing about these femtosecond lasers is that they deliver their power in a train of pulses. So we're talking 100 kilohertz nominally for these sort of systems. And the pulses are at least 200 femtoseconds short. So femtosecond is times 10 to the minus 15. It's an extremely short amount of time. And these pulses are only 200 femtoseconds. What that means when you look at the numbers is that, sure, we only have 400 microjoules per pulse, but that pulse is arriving in 200 femtoseconds, which means the pulse power actually gets up to 2 gigawatts. And that's an extreme amount of energy to be delivering in that very short amount of time. And then when you think about that you can deliver it into a focal spot of around 10 microns in diameter, the actual irradiance, so the amount of light flux going through there, gets up to a crazy number, like times 10 to the 19 watts per meter square. To compare that to what it's like looking at the sun is about a kilowatt per meter squared. So we're many, many, many orders of magnitude above the sort of irradiance you'd get by focusing the sunlight with a microscope glass. These energies are quite extreme. The interesting part of physics you probably heard about to great fanfare last year was laser fusion starting to get interesting. Okay, when you're talking about doing laser fusion, you're taking lasers like this, you're multiplexing them to get the energy from gigawatt levels up to terawatt and petawatt levels. So people are really doing some really extreme physics with these types of lasers. Okay. The other thing that goes along with this is beam delivery. There are several ways you might deliver the beam to your target with the laser. A really nice way of doing fast scanning and marking is to use galvo scanners. So these are high-speed mirrors coupled with an f-theta lens. You can also just direct right into the material using objective lenses. And then you can also use some more cleverly engineered optics like helical drilling optics. These will actually rotate and incline the beam for you to machine out, precision holes and let you create a whole raft of different features that you wouldn't be able to do with just an ordinary focused beam. So I better hurry up. So what might it look like? I might instead pop the browser. Whoops. Oh no, it's all closed up on me. That's okay. We'll go back to the talk now. So I will show these clips. So this is a little clip of what a process might look like. Jump forward for me, please. Please work. Why don't you want to jump forward? Sorry guys, just a sec. ticking over? Why does everything work in practice and not in presentation? It jumps and then it jumps back. I'll bring up some clips at the end. It's okay, great. I'll keep kicking on because what do we want? We want to get people off to lunch. I'll bring up some other clips at the end. So basically, you'll see the laser zapping around, marking some components. I will bring up a couple of clips at the end. What I want to say about the 2D process flow, yeah, but I've got a few more slides too. And I've got a few more video clips, so it's okay. You get the gist from it. So the process flow of how you're getting parts into manufacturing. Basically, you want to start with CAD design. So if there's any little course from the afternoon sessions that you take out of from being at the winter school, the little session on CAD work that Mark and the guys will be running for you, if you haven't really delved into doing your own design and stuff like that, get the motivation to do it at this point in your travels. While ever you have a university email, you can get all the Autodesk products downloaded on educational license for free. So it's a great time to get in and learn them. Because everything you're ever going to want to make or fabricate, you want to start with a design that you can pass on to the manufacturer or make yourself in the clean room. So, and the laser processing is no different. What we need from our users are DXF or DWG, drawn CAD files, which we can then go and apply laser parameters to and cut all the features out. Okay? But of course, lasers don't have to be used exclusively in 2D. You can do some 2.5D slicing to create sort of 3D objects. Of course, this is limited a little bit by the line of sight of the laser. But even so, you can make some slots, you can make some micropillar channels, you can make little holders like I've got there between two slides of glass. So you can take it out to the third dimension. And then more recently, our most recent toy is to bring in some additional axes to create degrees of freedom so we can do what's called 5-axis processing. So this is so we can actually manipulate the part in 3 dimensions and do laser marking and laser marking on either side. Okay, so this one's going to play. We took delivery of this machine just in December, so this is new for us, and this is just a very quick construction clip of what it takes to put an instrument like this together when it has to be taken apart to fit in the lab. Okay, this is not ideal. If you're building like nice clean room material, hopefully someone's designed the clean room doors to fit the instruments in. In this case, we couldn't quite make it. So this dedicated team from Pulsar Photonics, the company in Aachen in Germany who has built our most recent machine, they spent a course of about 2 weeks assembling it almost component by component so it could come into our lab. So it was a real mammoth effort. And so hopefully this video clip plays straight up. Spacebar again. Yep, okay. And so this is a look of the new machine sitting inside the lab. You can see there the black optic sitting up the top. That's the Gavo optic that I talk about. The nice thing about this machine is that the whole machine is emulated in software. So it knows what it's doing. It protects itself from collisions and things like that. And then I have and I don't have these videos completely synced up, but this is the idea that everything you're doing on the machine, it's emulating in the software environment for you. Jogging back and forth. Yep, not completely synced up. And just as a little example of the 5-axis capability, this is just a little example. We have a little octagonal trinket, right, like a glass keyring. It's a nice demonstration because it has all the different facets. Use camera systems to align to it. We'll also have a touch probe. These are elements of machining that Mark will probably do a lot better job on in his presentation tomorrow. But yeah, we need to align to components on the machine. That's why you see a slight offset between the grey and the green object, right? The green is where it's actually sitting, and the grey is where we put in the machine in its approximate position. And then you see the machine go ahead and mark this with the laser. So it's coming along, it's positioning the object under the scanner. There'll be a little ball of plasma. It's a bit easy to see the ball of plasma on this next one where it tips up. So that's the sort of idea of the machine running. Now the thing is, this is a fairly macro sort of object. The idea of this machine is that we can actually get down and do some fairly small features with this type of caper. All right. Just to charge through a few results, some of these are old, some of these are new, but it ties together a few of the different fabrication techniques we've spoken about in the last couple of days. This is an alternative, like Mike talked about doing etching of via holes in thin glass. We do this for some other projects using laser processing. The laser technique I'm going to show you, it's not really compatible with a high-end clean room technique. But when you're making little membranes that require little holes in it, this is one of the applications where lasers really are helpful. You don't necessarily want to go through the whole process of designing lithography masks and doing resist and stuff like that just for a little membrane that's going to be used disposably. Whereas in a matter of a few minutes, we can drill a hole of micropores in these membranes to do that. This example was used by a researcher that uses both the facilities here at ANFF-SA and our laser facilities to get his devices together. It's a microfluidic separation between these pores. So you'd have one side of these would be a hydrophobic, one would be hydrophilic, and they can separate the species through the pores by that way. That's one example. Heike already showed this one this morning, but I think it's a great one. It shows how many people come together to get stuff to work. The optical fibre here is designed and extruded at University of Adelaide. You'll see some of those facilities tonight. And the laser machining, like Heike said, is used to make the grading. So they are single shots on the fibre. Each shot is about 600, 700 nanometres in size. So that's sort of the feature size you can get to when you're using a microscope objective focusing these sort of lasers. You get down to that sort of sub-micron resolution. Okay. One of the key customers, besides microfluidics and stuff like that we get using our facilities are people working on photovoltaics. Lasers are becoming very popular in photovoltaics for many applications. Some of the more CW ones are used for doping the silicon. Okay, so you can use the laser to melt the surface of the silicon to introduce dopants. What we're mostly concentrating on with the short pulse lasers is machining off the insulating layer, so the silicon nitride, the dark layer on the surface. And we want to do that in a way that does not damage the underlying silicon. Okay, we don't want to melt or disturb the doping underneath. And so with a well-tailored process using an ultra-short laser, you can just sputter away the silicon nitride layer and not damage anything underneath. So these, you know, lasers have been used in photovoltaics a lot, but these short pulse lasers are really finding a home on some of these processes where you want to do selective material removal. What else do you have hiding in here? Oh, I just want to allude, yeah, with our lasers we can machine soft materials. So we do work in PEEK and Captain and even softer materials like PVDF, which is an electropolymer, sort of like those Octo robots that Michael showed you in his video the first time. The lasers can be machining those materials. Where it's really good is for machining very brittle materials. Okay, this is a piece of graphite, and you really don't want to take any sort of other tooling to graphite. It will just tend to fall apart on you. That piece that I'm showing there, it's about 1 centimetre in size. So all those little channels we've machined in it are quite fine, and the graphite stays together as long as you don't squeeze it too hard with a pair of tweezers. And also another example I have there is where we've actually taken samples of coal and machined fluidic channels in it. Right, so this is called coal on chip. This was people studying the way that fracking chemicals might migrate through the seam and things like that in a microfluidic way. Okay, you don't want to take a big lump of coal into your clean room to do a DRIE process on it. I'm sure the people would kill you for doing that. But with a laser, we can go and etch these channels in directly and actually get some of these more exotic ideas together. We can machine very hard materials. We do quite a lot of work in ceramics. A lot of them are alumina ceramics, but we've also done jobs where we've machined some nasty ceramics like boron nitride. Again, doing this sort of stuff would be very hard on mechanical tooling. It's one of the advantages that the laser has. You don't have any tool wear. You just need to throw more laser pulses at it, hopefully. And of course, we can machine the very hard materials. Okay, we've had several projects come through where we've been drilling via holes in diamond, scribing up diamond substrates, and that sort of caper. To tie in with the presentation from Scott this morning, this is an example where a wafer would need to go through several processes, including a laser processing step up with us. Again, when we communicate the different steps of these design, we're passing around these DXF and CAD files. And so, unfortunately, if you're going to be in microfabrication, some of your life has to be dedicated to managing your AutoCAD and your DXF and CAD files. So get a lot out of that session if it's new to you. So this is an example of a wafer full of Scott's hydrophones. Okay, so we're making 23 or so at a time, and this is just the substrates on which the optical fibre would be laid. So there'll be etching processes that need to be done here at UniSA. The step that needs to be done with the laser is we need to bring them down, we need to cut great big through slots through the wafer. And these are features which are much larger and much coarser than any of the lithographically defined and etched features on there. So we're cutting like 14 millimetre long slots, which are about 1/2 mil wide, in 2 places. You can see on the bottom right there, they're the 2 open slots. We're looking through the wafer onto a piece of tissue paper underneath. It's a very, very expensive, very hard process to do with chemical etching. Okay, it's a very long Bosch process to eat out that much silicon. But because of the use is not there to be particularly clean or anything. It's just there to create a separated bridge of silicon. The laser has been the ideal tool for going and machining these out. So just one little example of a project which gets passed around within the ANFF network and using different techniques to make different style of features. And in the end, this is hopefully helping Scott scale up his hydrophone fabrication. Okay. The last one I'll mention is Microex, a company here at Flinders. They're down at Tonsley. Microex has been working for a good long time on really compact, novel X-ray sources. As X-ray detectors have gotten much, much better, the X-ray emitter can be scaled down and actually use some pretty novel materials like carbon nanotubes as the emitting material. But the one thing that your X-ray tube does need, it needs a high voltage mesh, a high tension mesh or a screening mesh. And that needs to be cut from tungsten so that it survives all the electron current in the vacuum tube. Machining tungsten is not fun. It's a very dense material. It's very hard on tooling. And the feature sizes that these guys need are sort of down of the order of a hair diameter. So they want to leave little wires behind which are 60, 70 microns. And that's where the laser machining has really sort of stepped in and made those components possible. So it gives you a little idea of some of the neat designs they've looked at. Okay, these are all machined out in tungsten using the ultra-fast laser process. It's not super fast. Some of these components still take about half an hour or so to etch out. But the results are really good, and it's very difficult to fathom doing it another way. Mark can tell you a little bit about the hours which were estimated. Yeah, so yeah, it was a bit of a nightmare job. But this is where the technology that I've hopefully introduced you today, this is where it really shines, in these sort of components and difficult materials. Okay, it's an example of the sort of finish we get on there. Reasonable sort of edge finish, and it's actually quite good for a challenging material like tungsten. Okay, what have I got? 8 minutes. I'll see if I can launch one of these. There are a couple of really other niche applications in, yep, it's going to pop up here. Oh, I'm going to get an ad on YouTube. Ignore that for a sec. Right. Now it's going to play for me. I'll pop it up here and full screen it. Okay. So there are other couple of really niche applications of these ultra-short pulse lasers in advanced manufacturing. This is an example of cutting tempered glass, and this is used in nearly all your mobile phone screens and things like that. The problem with tempered glass is that it tends to want to shatter when you touch it mechanically. And so this is a really neat use of laser dicing, where you can actually cut through the glass from the inside out. And I've got a couple of little examples there. You see that one's a bit sped up, but yeah, so this is focusing the laser inside the transparent material and cutting the glass from the inside out, and it's only really possible with these short pulse lasers with these really high intensities. So this is a really neat technology that's really helped make the mobile phone and the display industry sort of take off as well. And I think on that note, I'll leave a few minutes for questions and let people get to lunch. I hope that was a good introduction to the sort of technology that we get to play with. And yeah, happy to take any questions if that got anyone curious. Cool.
Thank you very much, Ben. Fascinating talk. Any questions from anyone online or in the room? Nothing online yet. Any questions for Ben? Ben, I'll ask a question. Just at the end, you showed the YouTube video, and it looked like the laser did its route, and then it was a quick fracture. Is that a thermal effect, or is that just?
It depends on the glass. So some of the real strongly tempered glass, like Gorilla Glass, the laser cleave will actually self-break, and you can actually make it help along a little bit just by blowing on the glass.
Amazing.
It's a good trick that they do at trade shows. The first clip I showed you from the coherent system, it was cutting slightly thicker glass, and it is actually a two-step process. So what you might have caught there, if you're watching carefully, the femtosecond laser runs around first, and then the CO2 laser, which is invisible, comes along and just heats that crack.
Right.
And the thermal shock from the CO2 laser will complete the cleave. So they're pretty clever systems. Yeah.
More questions? Yes.
Hello, thank you for the call. I have a question. If I have a really sensitive to temperature material, could it be could I use the laser but without destroy the temperature?
Yeah. You do have to be careful. If we're talking thin film sort of piezo materials, then yeah, we've managed to do that. That is a request that comes to us on occasion. Where it works well is if it is sort of a film sort of style material, because then, yeah, we can laser some areas away, and because the laser will not be transferring too much thermal energy into the surrounding material, the majority of the piezo material will still be okay. And it's the same for semiconductor and other materials as well. We've had some success processing those materials where the user was concerned about thermal issues. And yeah, it goes okay. You might find some sub-micron area of the material that's a little bit denatured, but overall, it'll be preserved.
More questions? Yes.
It's a really nice presentation, and for the fiber brag breaking ANFF, so you show a figure and the scale is 2 micrometers. There are some holes in there. So what's the size of your...
Yeah, about 600-700 nanometers. 600 or 700 nanometers in diameter. You see those guys? Yeah. So the thing, we're machining those little dots with a green femtosecond laser. So the theoretical diffraction limit of that laser can be down under 400 nanometers, something like that. So we're still able to make shots which are sort of twice the diffraction limit and control that reasonably well, which is small enough for doing Bragg grading features, right? The period of a Bragg grading needs to be around a micron, 1.5 microns, and we can just get those features nicely at that size with the laser to put those features in.
Okay, we still have yes question.
Only if we had time. That was a great presentation. I was just wondering if you could elaborate just on the micro X slide when you mentioned the CO2 X-ray sources and solutions. I was just wondering why you were interested in using carbon nanotubes within this.
Or you'd probably have to check the MicroX site for the full story. It's just that as the exotic carbon materials were discovered, the graphenes, the carbon nanotubes and things like that, they became really efficient sources of hot electrons. Okay, they're better than the old traditional tungsten filament, right? A conventional X-ray source or X-ray tube or something like that, they'd be getting their electrons from a heated tungsten filament. But you can get a lot more electrons from a lot smaller space using these exotic carbon materials. So that's the novel part of MicroX's technology. But then the challenge is everything else that goes along with the X-ray tube needs to be miniaturized. So, you know, you go into an X-ray system in the hospital, it's quite a big system, right? MicroX is now building a whole X-ray sort of system, which is sort of almost, you know, a couple of shoe boxes in size, using that stuff. So there will be more story about MicroX's journey on their website. But yeah, there's a whole bunch of interesting material science that goes around as to why they've focused on these carbon materials and how that's allowed them to miniaturize the X-ray source.
And if you do have more questions there, we've got plenty of contacts with people that you can chat to, so we can definitely put you in contact with them.
Question here?
The one problem that we face, as I'm from parameter engineering group, and the one problem we face is the fabrication tolerance. Means that if we design the holes very closely spaced to each other, the major problem is fabrication tolerance. So my question is that what is or how much the percentage of fabrication tolerance the laser that you have shown in the presentation?
It's never really go beyond par with a nice lithographic process. Okay, if you take a nice Heidelberg mask writer, or if you go extreme and go to an EBL type system, you're always going to do a little bit better. But what our lasers do have, they have quite good precise motion systems on them. Okay, On one of our systems where we're using the microscope objective to do things like write the Bragg ratings and things like that, they're running air-bearing stages which have 4 nanometer encoders on them. So that gives us some sort of faith that when we tell the system to go somewhere, it's doing it within 10 nanometers or so. But then you have to worry about what's your laser going to be doing. Okay, so laser beams can drift around a little bit over the course of some time. Generally, what I say when we're making components like the tungsten components, we say that we can make them to within about plus or minus 3-4 microns. We can repeat the tolerance. But if we had someone that wanted to be doing like micro pores in glass, so they wanted, say, 3 micron pores on a bit like a 10 micron pitch, then that would be extremely challenging to do with the laser technology. So it really depends. I mean, you can float some dimensions by me at lunchtime and see what makes sense. Yep. And we can have a chat to see whether it might be feasible to have a look at that. But yeah, it's a reasonably precise manufacturing technology, but it may not really compete with lithographic sort of tolerances if that's where you need to be.
Okay. Well, with that, we're...
Was there one online?
Lightsaber question, that's right. Yeah. So is there a Star Wars fan online who wants to make a lightsaber and would like your help?
Yeah.
What do you reckon?
Yeah. No. I mean, the lasers are getting quite interesting as directed energy weapons, but to have one you want to be safely holding you in your hand, I don't think that's really the go. The best emulation of a lightsaber I have seen are some of those little plasma torches that people make. So, but then you have to walk around with a barbecue bottle next to you. So, you know, yeah, no. The laws of physics sort of discount a real lightsaber ever being on the market. Yep.
That's the saddest news we've heard today. Ben, thank you so much for your presentation. We have a small gift for you. So I'll just grab this while here. So yeah, thanks again, Ben. And just remember, Ben says when you use your lightsaber, wear your safety glasses.
Yes.
Okay, not like Luke. So we have, so to those of you online, thank you very much for joining us. Because you're not here physically to do the pracs, this is the end of the day for you, but thank you for joining us. For those of you who are joining the Rapier tour, it's at 12:30, and so, you know, don't wander away from lunch because you might miss your tour. For the New Zealand participants, Belle is stalking you once again. She'd like to get a photo of you as a group. So if you can just turn left and go outside just before lunch, she's going to take a quick snap of you. You'll be all over social media before you know it. Also, for tonight, for the Optofab tour, just remember that the mini taxis will leave at 5:30 p.m. For the Optofab tour. So please be on time for that so that it doesn't delay. Yes?
Is it right that we need to sort our own
so the taxi cabs will take you there?
So that's the way there, but once the tour is finished, you're set loose from Adelaide to do whatever you want to do to Adelaide. We won't get you back to Mawson Lake, so just letting you know. But look, just to finish off the morning before we go to lunch break, I think you'd agree that the presentations this morning were really fantastic. We've seen a lot of light in different areas, and so can you please just thank all the speakers, including our insights. Okay, see you at lunch.
Just a little bit of new content. Some old stuff too. Yeah, all right.
It's really great. Fantastic. So, yeah, thanks again.